Salutations, my fellow computer-touching homunculi. This is 14 longest common prefix. This problem, not gonna lie, kind of pog. First time doing it, not gonna brag. I kind of dry runned it, boys. First try, optimal space and time complexity. So, kind of feeling like my brain is kind of massive right now. But I'm going to draw it out. So we're going to walk through the problem. What does it mean? Then we're going to go to Sketchpad. I'm going to draw it out. And then with a double reinforcement there, you should be able to implement it on your own. So write a function to find the longest common prefix string amongst an array of strings. If there is no common prefix, return an empty string. Pretty straightforward question here. Right? But if we take a look, right, at the examples, what do they mean? So they're saying that we're passing in strings, which is an array, to this function, and we're given flower, flow, and flight, right? So what is the longest common prefix they share? Well, it's not flow. It seems like that if you go through the first two strings, right? But then you get to flight and you realize the only thing all of these strings share in common is FL, right? And then we look at strings again. This time you have dog, race, car, and car. These have no common prefixes, right? Just from looking at the first character, you can tell, right, that these have no common prefixes, right? So how do you go about this? So what's the intuition for the problem? So boom, we're going to jump right into Sketchpad, right? And we have no space. So I have an array here above, right? And so how would you go about solving this? So what you can do, right, as a very simple problem, right? Usually, right, if you want to maximize or minimize something, you can do it on the first run, right? Why is that? Because you can do it on the first run and commonly in linear time, right? Why is that? Because you're going to see all elements in the array or list, right? And so you should be able to apply some, comparison criteria here, right? And then take that naive approach all the way down to the solution, right? Kind of like finding the minimum element in an array, right? So how would you find the minimum element in an array, right? So if you wanted to find the minimum element in an array, right, couldn't you just assume, like, so humor me here, we have another array, right, called num, and it's just going to have 1, 3, 5, and -2. So you want to find the smallest number in this array, right? How would you do that? You could sort the list, right, in descending or ascending order, whatever, and you could take the first element, right, and that would give you the smallest element, right? But commonly sorting out of those are going to end you with n log n time. And you can do this in linear time, right? So why do it that way? So how do you do this, right? So if you want to find the minimum number in an array, what you could just assume, we're just going to say smallest, right? Just assume, right? We're just going to assume that the first element is the smallest element we've ever seen that will ever exist in this array, right? Just assume the first element is the smallest element, right? Why is that? Because we can just continue this linear comparison down the array, and then we'll find the element that is the smallest. So now we're at 1, right? So before we even start the array, we're just going to say 1 is the smallest element in the array, the first element in the array, right? So now we're going to iterate through the list, right? And so this is going to include the first element, even though we chose the first element as the smallest element. So is 1 less than 1? No, right? But it doesn't matter. They're both 1, so we're just going to say 1. Is 3 less than 1, right? So is 3 less than 1? No, right? So is 5 less than 1? Is 5 less than 1? It's not, right? And then we go to here. Is -2 less than 1? Yes, it is, right? And there you have the answer. So what does this mean for the problem we're doing here, right? So it's the same thing that we're doing here, right? It's just going to be a little bit different. So we're going to say longest, I'm just going to call it LCP. We're just going to assume, right, before we even iterate through the array, obviously our array can't be empty. We're just going to assume, right when we get started here, right, that our longest common prefix is the first element in the array. Just assume, right? And then you're going to see, right, that it's the same algorithm as the previous problem. It's just a little bit different. So just assume that flower is the smallest element in the array. Right? So now we're going to iterate through the array. So we're going to say, hey, does flower, the first element in the array, share a common prefix with flower, right? And so our longest common prefix, right, is 5 characters long. this is, I mean, it's not 5 characters. It's 6 characters long, right? FLOWER. And if we just check our longest common prefix, right, against this string up here, which is our first string so far, right, we'll see that obviously they're the same string, so their longest common prefix is going to be flower, right? And that's great. So we'll just continue. So now we're at flow. So now we're saying what's our longest common prefix so far? We're at the second element in the array, right? So this is where it gets a little bit different from the minimum of that array from before, right? So now we have flower and flow, right? So basically what's going to happen is in our loop, right, we're going to have an inner loop, right? And what's our inner loop going to do? Our inner loop is going to try to find the longest common prefix that they share, and it's actually really simple to do, right? So if we assume that, you know, we're currently working with our longest common prefix, right, we're just going to say, hey, if these two numbers, if these two strings they don't share longest common prefix, we're going to remove letters from the end of our prefix until they do, right? So we started with flower. Is flower a longest common prefix between both of these, right? It's not, right? Well, then let's remove one element. Let's remove the last character in flower. So now it says flow with an E. So is flow the longest common prefix when compared to flow? It sounds the same, but they're not. They're still an E, right? So you know what we're saying? We're going to remove the R, we remove the E, right? So now we're going to have FLWO. So is the longest common prefix flow the same common prefix that is shared with flow? We're going to say, yeah, that's dope, right? And so we can move on to our next iteration. So now we're at 3. So now we're at flight, right? And you can kind of see where this is going, right? So we're going to say, hey, is the longest common prefix so far, is it the same prefix in flight? Well, it's not, right? And how do we check prefixes? Well, we know that our longest common prefix, right, is 4 characters. So we can just say, are the first 4 characters in our current string equivalent to our first 4 characters in our common prefix, right? They're not. So what are we going to do? We're going to remove 1 character from the end. Now we have flow without the W. Is our common prefix of 3 characters, does it exist in flight? It doesn't, right? What did we say we'd do when it doesn't? We said that we would remove a character, right? So now you can clearly see where this is going. Now we're at flow. I'm just going to move my camera just so you can see a little bit. Now we're at flow, right? So how do we make sure? So now we're at flow, right? And we just did O. So we're going to cross out. We're going to say, hey, we crossed out flow, right? So now this is just going to say, I don't know why I wrote the O. It's just going to say FL. So does our current common prefix FL exist in flight? It does, right? So we did great. So how does this return empty strings, right? So humor me, if we add, let's just say, dog at the end of this, right? Just assume it's there. We're going to say, hey, does our common prefix FL exist in dog? Well, it doesn't. What did we say we would do when that happened? Remove a character. Now we're at F. Does our common prefix F exist in dog? It doesn't, right? Now we have nothing. And so since our inner while loop, right, it's going to say, hey, if I'm ever empty, there's no common prefix, right? So we can just return false. I think we're supposed to return a Boolean. Or you're supposed to return an empty string, right? And so that's the intuition for this problem. And so we can just do that, right? So what we can say first, right, is that if there's no common prefix, return an empty string. Well, the first thing we can say, right, if the string is empty, right, then there's no common prefix, right? It just is what it is. The string is empty. So what common prefix, the string list of arrays is empty, list of strings is empty, there's no common prefix to be had, right? But then we said, well, that's okay, right? We would just iterate through the strings, right? Right, but before we would do that, we would say, hey, let's just assume, right, that our LCP, which is our longest common prefix, right, let's just assume that it's the first element in the array of strings, right? And then we're just going to say for let, we're just going to call it word. I don't know what to call this, so we're just going to call it word. Boom. So let word of strings, right? So our current, whatever current word that we're on, right? We're iterating through all the words, right? So we said, right, that this is going to be just kind of keeping a running longest common prefix, right? And we said that the major part of that, right, was asking whether or not, right, that two strings shared a common prefix, right? And if they didn't, we'd continue to remove elements from our prefix until they did, right? So we can say right here, right, we're going to say while, right, and what's our condition here? We're going to say for one, right, we can't check if they share a common prefix, right, if the string is empty, if our least common prefix is empty, right? So if LCP, right, does not equal 0, and here we're going to actually check, right, if they share a common prefix. So how do we do that, right? So we can just say, right, is LCP, right, our longest common prefix, is it equivalent, right, to word, right, which is our current word that we're iterating through of the strings array, right, dot substring, right, and here we're just going to take the 0th character, right, up until the LCP.length character, right? So if LCP has 3 characters, right, we're going to go from, we're going to take the 1, 2, 3, first 3 characters of the word to see if they have the same prefix, right? And if they don't, right, this was the major part, right? So we want to not this whole thing right here, right? Because this loop, right, only runs while they don't share a prefix, right? And what did we say we would do when they don't share a prefix? We would just remove the element at the end, remove the character at the end of our longest common prefix, right? So we're just going to say LCP, right, is equal to LCP.substring, right? And we're just going to say, give me the first character, right, all the way up until the LCP.length minus 1 character, right? So we're just going to remove the end character, right? And this loop is going to run until they share a common prefix, right? If that's the case, right, if LCP gets out here, right, and its length is equal to 0, what does that mean, right? It means that the current LCP that we're at, right, like we said we had dog, right, once we had FL and we were working with dog, right, it just completely ran out FL, it became empty, right, because they just don't share a common prefix, so it's going to be empty, so we're going to just return an empty string, right? And then once we get out here, what we'll do, right, is we can just say, we can just return LCP, right? And if we run this, it works, and if we click submit, it doesn't work. Output false. Oops, up here I put return false. We're supposed to be returning an empty string. So we can click submit, and boom, there you go, right? And so what's the time and what's the space complexity, right? So if you take a close look, right, we're iterating, right, straight through strings, right? It might be intuition, right, to say linear time, right? But that's not quite the case, right? What we're actually going to be bounded by, because we're comparing all of these, so the string comparison here, right, is going to be done in linear time, because we're literally comparing strings, right, even though it's kind of hidden in this equivalent operator here, right? Which means that the number of operations in the worst case, right, is if we have flower, right, if we have a list of strings, right, and all of them just say flower, right, it's just flower, 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 which means I will have to iterate, right, 6 characters, right, for every element in the list. And so the time complexity here is actually going to be S, right, where S is the sum of all the characters in the list, which will also give us the total number of operations that we would have to perform to complete the longest common prefix. And the space complexity is going to be constant space, right? There's no major data structures we're using here. We're not, our variables that we're using to complete this algorithm, right, they're not going to scale with input to the function. We're not using any recursion here, right? And so any of the common indicators for constant time here apply. And so this is going to be, constant space. This is going to be constant space. And so this is longest common prefix.